In this video, we're going to work example problems related to quantum theory. So everything we learned about quantum theory, the development of quantum theory. Also, as a preliminary, we learned about electromagnetic radiation. So we'll have problems involving electromagnetic radiation as well. Okay, let's get started. What are the units for wavelength and frequency of electromagnetic waves? What is the speed of light in meters per second and miles per hour? So, okay, an electromagnetic wave is a wave like any wave. A typical wave that you learn about in physics, so like a water wave, right? It's a wave. So the units for wavelength are length. So you could have a wavelength be in meters, in feet, whatever. It's just it's the length that the wave repeats. A wave is periodic. So this wave starts over at this would be the wavelength. It's a distance. Okay, what frequency? That's 1 over time. Typically it's 1 over seconds, like hertz, but it could be technically be 1 over any time, like 1 over hours, 1 over minutes. And it's 1 over a time because you think about this as it's one cycle in how much time. Okay, what is the speed of light in meters per second? The speed of light in meters per second we know is 3 times 10 to the 8th meters per second. Now, if we want that in miles per hour, then we just do a conversion. We say 3 times 10 to the 8th meters per second. So let's get that to hours. You've got 60 seconds for every 1 minute, and then 60 minutes for every 1 hour. So now we're in meters per hour. Now, if I use Google, I see that there's 1,609.34 meters for every 1 mile. Okay, and so now we are in miles per hour. Well, let's let this miles in the numerator and hours in the denominator. So we've got 3 times 10 to the 8th times 60 times 60 divided by 1,609.34. So 6.71 times 10 to the 8th. Miles per hour. And there we go. Give the high and low wavelength values that define the visible region of the electromagnetic spectrum. So here is the electromagnetic spectrum. It goes all the way from like nuclear decay, gamma rays coming out of a decaying nucleus, all the way to radio waves. It's the entire spectrum here. It's all of these. This is all electromagnetic radiation. It's the same physical thing here, electromagnetic radiation. This propagating electric and magnetic wave that's like perpendicular to one another. But the only difference here, like the electromagnetic waves in general all propagate at the same speed, the speed of light. But the difference here is the wavelengths or the frequencies, which are like kind of tied to each other. If you set a certain wavelength, then you automatically set a frequency and vice versa. And so now there's this small region here that's the visible light region. The entire spectrum is a little region in here that's the radiation that we can see, right? We can't see heat waves like other animals can. So what they're asking is, what's the upper and lower wavelength values for the visible light region? So they said wavelength, not frequency, and so there you go. It goes from 400 nanometers to 700 nanometers. So 700 nanometers to 400 nanometers. Give two everyday examples that illustrate the concept of quantization. Yeah, so money is a good example. You can't have money that's like a fraction of a penny. I think haven't they done away with the penny now? It's only like a nickel now, maybe. But I can't give somebody a half a penny in terms of money. It's quantized, right? Steps are quantized. I can only go when I'm climbing stairs. I can only go these quantized distances up or down. So money and steps. What is the frequency of light having a wavelength of 456 nanometers? What is the wavelength in nanometers of radiation having a frequency of this many hertz? Okay, this is the type of radiation used in microwave ovens. I guess they're talking about both of these. I'm not sure, but yeah, so this is easy. When you're thinking about electromagnetic radiation, or really any wave this applies to, the speed of the wave is traveling is equal to the frequency times the wavelength. And the way you can remember this is frequency is 1 over time. Wavelength is a distance, so you're left with length per time. That's velocity, right? The speed. Well, what's nice about electromagnetic radiation is the speed is constant for all electromagnetic radiation. So since the speed is 3 times 10 to the 8th meters per second, let's keep that in mind, then, well, okay, in nanometers, that would be what? So let's see, this is meters per second. You've got 10 to the minus 9 meters for every 1 nanometer. So it's really 3 times 10 to the 17th nanometers per second. So I'll just leave it, the nanometers per second, off. And so now the wavelength, we've got 456 nanometers. And now we're wanting to solve for the frequency. So the frequency is, you've got 3 times 10 to the 17th divided by 456. And let's see, that would cancel out the nanometers, and we're going to be left with, this is in nanometers per second, so we're left with hertz, 1 over seconds. 6.58 times 10 to the 14th. One over seconds, hertz. So this is part A. Okay, part B, we've got, let's see, the wavelength is going to be the speed over the frequency. The speed is constant, so let's see, I can just leave this. Oh, they want it in nanometers, so let me put it into 3 times 10 to the 17th. That's nanometers per second, the speed of light, and then divided by 2.45 times 10 to the 9th. So we've got, let's see, 3 divided by 2.45, 1.22. So 1.22 times 10 to the 8th. And that's going to be nanometers. And there we go. How many minutes would it take a radio wave to travel from the planet Venus to Earth? All right, so let's see. Do we need to get the wavelength or frequency of a radio wave? I don't think so, because it's just the speed of light. All light travels at the same speed. So it would take the same amount of time for any electromagnetic wave to travel a certain distance. That's why the energies are different. If it takes a gamma ray, which has a much higher frequency, the same amount of time to go this 28 million miles, well, then it must be traveling as like a radio wave. Well, then it must be have a much higher energy because it's oscillating that fast and still going that same distance. So let's see, we've got 28 times 10 to the 6th miles times, let me make some room here, 28 times 10 to the 6th miles times, and then we've got 3 times 10 to the 8th meters per second is the speed of light. Okay, but now we need to convert this to, so 1609.34. Well, that's okay. I want to put that in the numerator. 1609.34 meters per 1 mile. Okay. So now we're in time. That's what we want, but they want this in minutes. So we have 60 seconds for every 1 minute. Okay. So 28 times 10 to the 6th times 1609.34 divided by 60 divided by 3 divided by 10 to the 8th. 2.5 minutes. The SI unit of length is the meter, which is defined as the length equal to this many wavelengths of the light emitted by a particular energy transition in krypton atoms. Calculate the frequency of the light to 3 significant figures. Okay, so it's just this formula for waves in general, the speed of waves relating their wavelength and related to their wavelength and frequency, but the speed of light's constant. So the frequency is just going to be, so 3 times 10 to the 8th. Well, okay, so let's see. What's the units of this? So, okay, this is kind of confusing. So when this electromagnetic wave travels this distance, what they're saying is that, and you might be saying, well, what's the units? Well, we don't know the units. It's just it propagates. It goes through this many periods, right? It's oscillating through space, and it goes through a cycle this many times. So 1,650,763.73 cycles, and that's 1 meter, right? So this light emitted by particular energy transition in krypton atoms, it comes out. And if you imagine it propagating through space. Okay, once it goes through its electromagnetic cycle, the electric cycle, the magnetic cycle, when it cycles through this many cycles, so 1,650,763, and then like 3/4 of a cycle. When it's gone through that many cycles, then it's traveled a certain distance in space. That distance is 1 meter. That's the definition of the meter. So, with that in mind, let's think about if we write this out. So 1,650,763.73 cycles times the fact that what? Well, this is cycles per meter, per 1 meter. So now we can say what? We can say we have 3 times 10 to the 8th meters per 1 second, because we know that's the speed of light. We know this is light for sure. It's light. So what are we left with? Cycles per second. That's frequency. So we've got 1,650,763.73 times 3 times 10 to the 8th. 4.95 times 10 to the 14th. Hertz. There we go. Consider the plots shown here for the photoelectric effect of two different metals, A, the green line, and B, the red line. Which metal has a greater work function? What does the slope of the lines tell us? So yeah, the whole idea here was with the photoelectric effect, when you shine a electromagnetic radiation on a metal, it ejects electrons. This is the whole story of the development of quantum mechanics. And it was Einstein postulated that it was you had like a stream of these photons. That's what light was. And so the whole what it ended up manifesting as is you have, if light comes in at a certain, the electromagnetic radiation comes in at a certain energy level, which Einstein said was equal to, you do Planck's constant times the frequency of the light. And this was a big statement here because it was based on this Planck's constant, that quantization of energy. Then if the energy of the incoming radiation was equal to the energy that binds the electrons in the metal, then that would be just enough to knock electrons loose, and that's it. They would just be knocked loose. But if you had even a higher energy incoming radiation than that, then it would knock electrons loose also with a kinetic energy. If it was less than the energy of the binding electrons, then nothing would happen, and it didn't matter how intense you made the light. If the energy of the incoming radiation was lower than the energy that binds the electrons, it doesn't matter how intense you made the light, nothing would happen. The intensity just means you were shooting more photons. So if you had let's say you had incoming radiation that was equal to the binding energy, so it would knock electrons loose and no more. Well, if you did a more intense light, you would just knock more electrons loose, but they wouldn't be all of a sudden, because you did more intense light, they wouldn't be coming out with more energy. No. And the work function was just a measure of how strongly the electrons are held in the metal. And what it came down to was the kinetic energy of the exiting electrons is equal to the energy of the incoming radiation minus the work function. So if the energy of the incoming radiation was equal to the binding energy, then the kinetic energy would be zero, but the electrons would be knocked loose. If it was greater, the incoming radiation energy was greater than the binding energy, then the electrons would be knocked loose with some kinetic energy. And so if we look at this plot here, we've got kinetic energy on the y-axis, on the x-axis is frequency. So, okay, this is in the right form. So if we think about this is like a y is equal to mx plus b. And so if we extend this down, the y-intercept, when the frequency is equal to 0, we've got, this would extend to here, this would extend down here. So the question is, which metal has the greater work function? Well, the greater in magnitude would be the red metal, the red line metal. It's going to take a higher energy radiation, a higher frequency, right? Planck's constant, that's a constant. So it's going to take a higher energy radiation to knock the electrons loose in this metal here. But if they just mean greater in terms of not magnitude, then I guess the green metal. Okay, now what does the slope of the lines tell us? Well, we can see the slope is Planck's constant, h. The blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency of about 7.5 times 10 to the 14 hertz. Calculate the wavelength in nanometers associated with this radiation, and calculate the energy in joules of a single photon associated with this frequency. Okay, so the wavelength, we have C is equal to wavelength times frequency. So the wavelength is the speed of light divided by the frequency. But they want it in nanometers, so it was, the speed of light was 3 times 10 to the 17th nanometers per second, okay, times, and then we would have 7.5 times 10 to the 14th cycles per 1 second. So there you go. That will be in nanometers. So 3 divided by 7.5, 0.4 times 10 to the third. Which is 400 nanometers. Okay, calculate the energy in joules of a single photon. So the energy is Planck's constant times the frequency. So Planck's constant is what? 6.626 times 10 to the minus 34 square meters kilograms per second. Okay, the frequency then is 7.5 times 10 to the 14th cycles so that per second. So kilogram meter per second squared, that's a Newton meter. So this is going to be in joules. So we've got 6.626 times 10 to the minus 34, and then times 7.5 times 10 to the 14th. So 4.97 times 10 to the minus 19 joules. What is the wavelength in nanometers of radiation that has an energy content of 1,000 kilojoules per mole? In which region of the electromagnetic spectrum is this radiation found? So, okay, we've got 1,000 kilojoules per mole. So let's do, you have 6.022 times 10 to the 23rd, or no, it would be 1 mole for every 6.022 times 10 to the 23rd of whatever this is. So that this is just going to come out to, you've got 1,000, and then I'm going to add 1, 2, 3, divided by 6.022 times 10 to the 23rd. 1.661 times 10 to the minus 18. Joules of energy here. Okay, we know that E is equal to HV. Let's keep that in mind. So, okay, let's put this here, 661 times 10 to the minus 18. And now let's write, so joules is kilograms. A Newton is kilogram meter per second squared, but then a Newton times a meter is a joule. So kilogram meter squared per second squared. Okay, now let's bring in Planck's constant. So we've got 6.626 times 10 to the minus 34, and the units of Planck's constant are kilogram meter squared per second. So kilogram meter squared goes away, and then we're left with just per second, which makes sense. We're in frequency here. Okay, so now we know we've got this lambda v here for the speed, relation between the speed of light, wavelength, and frequency. So we want to get to wavelength. So all we're really doing is, if we bring in the speed of light, so 3 times 10 to the 8th meters per second. Now this cancels. We're left with 1 over meter. But then we can just take the reciprocal of this, because it would be like, what that means is, what we have is, we've got, so V over C is equal to 1 over lambda. That's in essence what we have here. V over C is in units of 1 over length. We just need to take the reciprocal. So, and that's going to give us the wavelength. But let's also do this. There's 10 to the minus 9 meters for every 1 nanometer. So let's do that. So we've got 1.661 times 10 to the minus 18, okay, divided by 6.626 times 10 to the minus 34. Okay. Then divided by 3 times 10 to the 8th. And then times 10 to the minus 9. Now we need to take the reciprocal of this. So 120 nanometers. Okay, now what region of the electromagnetic spectrum is this? That's right around in here. This goes to 400. Okay, so we're in, or no, we're not in the visible light region. We're in like the ultraviolet region. A particular form of electromagnetic radiation has a frequency of 8.11 times 10 to the 14 hertz. What is its wavelength in nanometers and in meters? Okay, so we've got C is equal to lambda V. So we can say so 3 times 10 to the 8th meters per second times the fact that you've got 8.11 times 10 to the 14th cycles per second. And so that would be in meters, but then if we did, so 10 to the minus 9 meters for every 1 nanometer, we could get to nanometers as well. So we've got 3 times 10 to the 8th divided by 8.11 times 10 to the 14th. That's in meters. 3.7 times 10 to the minus 7 meters. Okay, now in nanometers, we just divide that by 10 to the minus 9. $370. Okay, so there we go. To what region of the electromagnetic spectrum would you assign it? So 370 nanometers would be in the just outside the visible light region, in the ultraviolet region. What is the energy in joules of 1 quantum of this radiation? So you do Planck's constant times, we'll do the wavelength in meters. Or no, wait. We need the frequency. So we have the frequency. So yeah, it's just going to be 6.626 times 10 to the minus 34, Planck's constant, times 8.11 times 10 to the 14th. 5.37 times 10 to the minus 19 joules. When light of frequency equal to 2.11 times 10 to the 15th, this is hertz, shines on the surface of gold metal, the kinetic energy of ejected electrons is found to be 5.83 times 10 to the minus 19 joules. What is the work function of gold? So it's the kinetic energy is equal to the energy of the incoming radiation minus the work function. So what they're saying is that the kinetic energy of the ejected electrons is equal to 5.83 times 10 to the minus 19, that's joules. And so now what is the energy of the incoming radiation in joules? We just do Planck's constant times this. So 6.626 times 10 to the minus 34 times 2.11 times 10 to the 15th. Okay, so 1.398 times 10 to the minus 18. That's going to be in joules as well, minus W. So we can see that W is going to be equal to, you take this and subtract from that 5.83 times 10 to the minus 19. 8.15 1 times 10 to the minus 19. Joules. Briefly describe Bohr's theory of the hydrogen atom and how it explains the appearance of an emission spectrum. How does Bohr's theory differ from concepts of classical physics? Explain the meaning of the negative sign in equation 7.5, the Bohr's energy level equation. So this equation. All right, so Bohr's theory of the hydrogen atom, what they're talking about here is that you have different substances have different emission spectrum, which what that means is if you take like a solid or a gas and you apply an electric current to it, or you heat it up and it gets to that glowing point, well, it's emitting light, right? And you could pass that light through prisms and try and separate out the different frequencies. And some like solids and liquids have continuous emission spectrum. They're emitting all frequencies of light. Well, let me clarify that. We're the emission spectrum, we're talking about visible light emission spectrum. We're just talking about visible light. So like solids and liquids, when you heat them up or pass electric current through them to where they're glowing, and you try and pass that visible light through a prism, it's emitting all frequencies of visible light. It's a continuous spectrum. But in certain circumstances, like with gases, relatively lower pressure gases, when you pass that, you heat it up, get it to a glowing hot, you pass that visible light through a prism, it separates out into these only discrete, specific frequencies of light are being emitted. So different substances, different types of atoms in the gaseous form have unique emission spectrum. Let me pull up a picture. Okay, so this is not a continuous spectrum. This is a line spectrum. It's like a fingerprint that you can use to identify different elements. Okay, but they were having trouble explaining the emission spectrum, coming up with a formula that explained where the emission spectrum were coming from. And all Bohr did was he used the whole quantization concept, the fact that Einstein had said that photons have these quantized energy levels based on E is equal to, what was it? No, it was HV, right? And Bohr used that to describe the physical nature of the hydrogen atom and come up with a formula for the emission spectrum. And what he said was that the electrons can only occupy these discrete energy levels. These quantized energy levels are around the atom. And he came up with a formula to where, you could only input N is equal to 1, 2, 3, 4. It's quantized, right? With this constant here that explained the hydrogen emission spectrum. It could model the hydrogen emission spectrum. Okay, now how does Bohr's theory differ from concepts of classical physics? Well, obviously it's very different. It's this quantized positions. I mean, you can't do that in classical physics. It's not like when you're driving your car around, you can only go at these discrete speeds. No. Okay, now the negative sign is just an arbitrary convention. He just assigned negative energies to electrons and atoms because in his mind, a free electron has more energy than one that's kind of contained around a nucleus. If an electron's around a nucleus, it's in a more stable state. Some copper compounds emit green light when they are heated in a flame. How would you determine whether the light is of one wavelength or a mixture of two or more wavelengths? Pass it through a prism. That's what prisms do. Explain how astronomers are able to tell which elements are present in distant stars by analyzing the electromagnetic radiation emitted by the stars. Yeah, they separate out the light frequencies. That's what this is all about. Even without being able to explain why these line spectra are occurring, you can still use these as sort of fingerprints to identify different elements associated with radiation. The first line of the Balmer series occurs at a wavelength of 656.3 nanometers. What is the energy difference between the two energy levels involved in the emission that results in this spectral line? Yeah, so with this formula representing the energy level of an electron around a hydrogen atom, the whole idea was that electromagnetic radiation is emitted if an electron transitions from one energy state to another. And then when that happens, the energy of the emitted photon is given by this formula. Okay, and then the Balmer series is just, so when you have like a map of all of the different ways that different photons that can be emitted from a hydrogen atom based on Bohr's model, you know, there's all kinds of different transitions you can make. They just labeled these different groups of transitions as different series. So here's some different series. These are different photons that can be emitted from a hydrogen atom, from going from n is equal to 2 to n is equal to 1, n is equal to 3 to n is equal to 1. So these are all transitioning from some higher energy state to n is equal to 1. These are all transitioning to n is equal from some state to n is equal to 2. That's the Balmer series. So what that means is that with the Balmer series, n final is going to be equal to 2. Okay? And now they're talking about the first line of the Balmer series. So that's going to be this line. So n initial is 3. Okay, now what is that R sub h? That is 2.18 times 10 to the minus 18 joules. Okay, so there we go. We've got 1 over 9 minus 1 over 4 times 2.18 times 10 to the minus 18. Yeah, and it's negative because it emits the photon. So minus 3.03 times 10 to the minus 19. Joules. Calculate the frequency and wavelength of the emitted photon when an electron drops from the n is equal to 4 to the n is equal to 2 level in a hydrogen atom. Okay, so we just use this formula. We've got Ni is equal to 4, Nf is equal to 2, and then R sub h is equal to 2.18 times 10 to the minus 18 joules. So let's see, we've got 1 over 16 minus 1 over 4 times 2.18 times 10 to the minus 18 minus 4.088 times 10 to the minus 19. That's joules. Okay. Now, the frequency is just you take this and you divide by Planck's constant, right? So divided by 6.626 times 10 to the minus 34. 6 point, I mean, we can, the negative doesn't matter. 6.17 times 10 to the 14 hertz. The negative is just telling us that it's emitted, not absorbed. So 6.17 times 10 to the 14 hertz. Okay, now the wavelength is just based on, so C is equal to lambda V. So take 3 times 10 to the 8th, 3 times 10 to the 8th, and divide this. 4.86 times 10 to the minus 7. Oh, we wanted nanometers, so that would be U times 10 to the 9th. 486 nanometers. An electron in the hydrogen atom makes a transition from an energy state of principal quantum numbers, some Ni to the n is equal to 2 state. So that's the Balmer series, right? All the transitions in the hydrogen atom that go from some Ni to n is equal to 2. If the photon emitted has a wavelength of 434 nanometers, what is the initial energy level that it came from? All right, so here's that formula. And so it's saying that NF is going to be 2. Let's see, R sub H is 2.18. Okay. So what's the delta E? This photon has a wavelength of 434 nanometers. So what's the energy of this photon? That's what delta E is. This is what was emitted. So the photon gets emitted based on this transition, based on whatever the energy of the transition is, the delta E. So we've got 3 times 10 to the 17th nanometers per second is the speed of light, divided by 434 nanometers. So that's the frequency. Okay, now times Planck's constant, 6.626 times 10 to the minus 34. So there's the energy, but this delta E is going to be negative because the photon is emitted. So we want to put a negative sign here. Okay, now let's divide this by that R sub H, 2.18 times 10 to the minus 18 minus 2.101. So what we have is this. 1 over n sub I squared minus 1 over n sub f squared is minus 0.2101. So let's add 0.25 to this. Now let's take the reciprocal, and that is Ni squared. So Ni squared is equal to 25.0628. So if we take the square root of both sides, put the plus or minus, but we're only going to want to keep the plus because these are like integers, positive integers. So it's 5. Ni is 5. How does de Broglie's hypothesis account for the fact that the energies of the electron in a hydrogen atom are quantized? Okay, well, de Broglie reasoned that if light waves can behave like a stream of particles, photons, right? That was the whole, after Einstein's theory that that light was based on the photoelectric effect, that it was a stream of photons, right? But then light also was clearly, it behaved like waves in some circumstances. Well, then they said, well, then we have to just think about it as light behaves in some circumstances like a wave and some like a particle. It has like a dual nature. Well, de Broglie said, well, okay, well then in that case, we can extend that same principle to matter, not just light. So electrons can possess wave-like properties as well. Electrons, which we classically think about as particles, right? Light we would classically think about as waves. So thinking about light as photons was kind of outside of the box. Well, de Broglie said, well, okay, well, we could do the same thing. Classically, we would think about electrons as these particles. Well, then let's go outside of the box and think about electrons as being like having wave properties as well. And so what de Broglie did was he looked at the dual nature of electrons in the hydrogen atom as like sort of like standing waves, which standing waves have the formula for standing waves has these quantized integers in them, right? The standing wave, it's not even a standing wave until you get to a certain frequency of the wave, then it becomes that classic standing wave. And then if you keep increasing the frequency, it just jumbles all over to nothing until you get to another quantized frequency. Then it becomes another kind of standing wave. And so that's how de Broglie accounted for these quantized energies of the electrons, because they had this wave-particle duality, right? It was like if you go to your physics book and you look at the formulas for standing waves, not even thinking about electrons, standing waves, if you excite the string or the rope at a certain wavelength or frequency, you get a standing wave. If you increase that frequency a little bit, it's a jumble of nothing until you get to 2 times that original wavelength, and you get a new standing wave. Then if you go 3 times, if you keep exciting it to 3 times the wavelength, then you get another standing wave. If you're not at one of these integer values of wavelength, then it does nothing. It's just a jumble of nothing. It only becomes this organized symmetric form here at these certain quantized values. And so that's what de Broglie looked at the electrons as possessing. They possess a wave-like property like this. If a hydrogen atom and a helium atom are traveling at the same speed, what will be the relative wavelengths of the 2 atoms? Okay, so yeah, what de Broglie stated was that matter has a wavelength associated with it. Even humans, right? That wavelength of matter is equal to Planck's constant divided by the mass of that matter times the speed at which that matter is moving at. Okay, so with that then, to answer part A, Planck's constant is constant, the speeds are constant, so let's do this. Let's divide both sides by, or multiply both sides by m, and we're left with h over u. So this is going to be a constant for part A, so what we have is lambda 1 times m1 is equal to lambda 2 times m2. So we can say that lambda 2 divided by lambda 1 is equal to m1 divided by m2. So what's the mass of a helium atom and a hydrogen atom? So the most abundant isotope of helium has a mass of 4.0026 AMU. So let's do 4.0026. Okay, now what about hydrogen? 1.007825. So 1.007825 divided by 4.0026. 0.25, about 0.25. So 4 then. For the wavelength of what is it? The wavelength of the hydrogen atom is about 4 times larger than that of the helium atom. Okay, now for part B, if they have the same kinetic energy being 1/2 mv squared. So what that means is that 1/2, let's say that 1 is hydrogen and 2 is helium. So 1/2 m1 v1 squared is equal to 1/2 m2 v2 squared. So the 1/2s cancel, and then we just did the m1 divided by m2, 0.251793. v1 squared is equal to v2 squared. So let's do, we could say, so v1 squared over v2 squared is this. That's v1 squared over v2 squared. Now, if we take the square root of this, that's v1 over v2. 1 point is about 2. So v1 over v2 is equal to 2. Okay, so if we do lambda 1 divided by lambda 2, that's what we're looking for. What we've got is h over m, let me do this. h over m1 u1 times m2 u2 over h. Okay, well, okay, let's actually do it the other way. Lambda 2 over lambda 1 is equal to h over m2 u2 times m1 u1 over h. These cancel. u1 over u2, that's the velocities, is 2. So 2 times m1 over m2. m1 over m2 was this. So you take this times this, 0.5. So now to make this a whole number, we can say lambda 1 divided by lambda 2 is 2. So in this case, the wavelength of the relative wavelengths of the two atoms is the hydrogen atom's wavelength is about twice as large as the helium atom's wavelength when their kinetic energies are the same. Which wasn't that the same? Is that what we got previously for part A? I think so. Maybe not. Protons can be accelerated to speeds near that of light in particle accelerators. Estimate the wavelength in nanometers of such a proton moving at 2.9 times 10 to the 8th meters per second. Okay, so we've got, once again, the wavelength is Planck's constant over the mass times u. So Planck's constant is in like kilograms, meters, seconds. This is in kilograms, so 1.673 times 10 to the minus 27 is the mass. Velocity is 2.9 times 10 to the 8th meters per second. So there we go. We've got, let's see, 1.673 times 10 to the minus 27 times 2.9 times 10 to the 8th. Okay, 6.626 times 10 to the minus 34 divided by this. 1.37 times 10 to the minus 15, and they want this in nanometers, right? So, okay, times 10 to the 9th. So 1 times 10 to the minus 6 nanometers. Okay, what is the de Broglie wavelength in nanometers associated with a 2.5 gram ping pong ball traveling at 35 miles per hour? So, okay, what is 35 miles per hour in meters per second? That's 15.6464. Okay, the mass, we want to put that in kilograms, so 0.0025 kilograms. And then Planck's constant is just the standard units. So we've got 6.626 times 10 to the minus 34 divided by 15.6464 times 0.0025. 1.69 times 10 to the minus 32. Oh, well, let's do that in nanometers. So times 10 to the 9th. 1.69 times 10 to the minus 23.